Hi friends, welcome to this class. So in last class we discussed the structure illustration of PGE1. Once they illustrated the structure and then they should synthesize this PGE1, right? So in laboratory how they are going to synthesize this PGE1, that is given by this E.J.Corey scientist, right? So here in this video we are going to study about E.J.Corey synthesis of PGE1, right? So what he did, he took this compound, from that he synthesized this PGE1, right? So different methods how he synthesized step by step, I am going to write it down, right? So if you see this is not aromatic, this is non-aromatic, but we know that stability order, you know, aromatic is more stable, then non-aromatic, then comes anti-aromatic, right? So here this, if I remove this proton, this carbon gets negative charge. So negative means 2, 4, 6 pi electron, it becomes aromatic. So what we do, these protons can be easily knocked out. So these protons will be always acidic. If you see this aromatic chapter, there they will tell if the compound is like this, these protons will be acidic because they are going to give aromatic compound. So here he used a base, sodium hydride, in presence of THF, tetrahydrofuran. It is a solvent, right? So this Na plus H minus, so this minus is there, right? It will take this proton H plus, so this electron density will be there on this carbon. So what we will get this thing, negative charge, right? So this is nothing but aromatic compound, right? So to this what they will add this MeOCH2Cl, right? So here negative charge is there, simply SN2 kind of reaction. This chlorine is a good living group, it leaves the system. So what we will get this structure. So what it is, now it is CH2OMe, right? So the structure we will get, right? So next step what he did, so here there are 2 and 4 pi electrons are there, that in conjugation, double bond, single bond, double bond, conjugation is there. To this he added alkene, C double bond C, having Cn at one side and having Cl at one side. So here we can see 4 plus 2 cycloaddition reaction. So conjugation is like this. So from here it will attack here to this carbon, and through this carbon it will attack to this. So can I write like this? So it is nothing but 4 plus 2 cycloaddition reaction, right? So this reaction is taking place at 0 degrees Celsius, and here also why this is taking place at 0 degrees Celsius, because if the temperature goes beyond 0 degree, that is at higher temperature, this compound doesn't exist like this. The compound will exist like this. OMe is there, right? So pi bond 1 is here, other pi bond is here, but it undergo isomerization and pi bonds comes here like this. So because of isomerization it happens when temperature is more than 0 degrees Celsius. So we maintain temperature at 0 degrees Celsius, right? And here it is 4 plus 2 cycloaddition reaction, and we will get this product C here, right? OMe here, pi bond comes 4 plus 2 cycloaddition reaction. So the arrow I have told, this pi bond shifts here, so it has shifted. This pi bond will react to this carbon, and this pi bond reacts to this carbon, and here Cn is there and here Cl is there. There is this possibility, and one more possibility is Cl will be here and Cn will be here, right? So isomers, so they are going to separate them there only, right? So since they are separating, let me give it only by arrow like this, where I am not going to mention any stereochemistry. This arrow, wavy arrow we call, this arrow represent whether Cn will be above or below, like that. It is separated, right? So this structure, can I write like this? The same structure I will write like this. See, this is a 5-membered ring, right? 5-membered ring. So I will write 5-membered ring like this, right? So this is my 5-membered ring, and here, right? So this is 5-membered ring, right? Yeah. This pi bond, let me show it here, and here OMe is there, CH2OMe. So I will show this CH2OMe, right? So 5-membered ring, here pi bond opposite carbon, it is having CH2OMe. So I have shown it, and other side these 2 carbons are there, which is attached to these 2 carbons, right? So these 2 carbons are attached to like this, and here I have Cl and CH2CN, right? So with wavy arrow, Cn and Cl, right? Cn and Cl. So this the same structure I have written like this, right? So if I directly write from here to this, you will get confused. So what I have done, the reaction I have shown like this, 4+2 cycloaddition. So I have written it nicely like that, right? So because here it is going to form 5-membered ring, so this is 1, 2, 3, 4 and 5, 5-membered ring, and here 1, 2, 3, 4, 5, 6, 6-membered ring, 1, 2, 3, 4, 5, 6, like that I can show. So this is how it is a bicyclic compound, right? So once we got that structure, then what they did, they added to this only, they added KOH. Along with me, you please write it down. And H2SO4, sorry, not H2SO4, H2O, water in presence of DMSO, dimethyl sulfoxide we call, right? So here what we will get, let me rub it. Yes. So what we will get is that, so this Cl is there, right? So in presence of water and all those things, that will be converted like this. See, this is 5-membered ring, and here CH2OM is there, and this Cl and Cn is converted to ketone, and pi bonds remains as it is. So this is the reaction when we add KOH, H2O and DMSO, right? Further what happens? See, here in next step they are going to add some oxidizing agent, that is MCPBA. You should know the structure of MCPBA. Metachloro per benzoic acid. Benzoic acid means COOH is there, but per acid means OH. COOH. This oxygen bond is there, right? Peroxide bond we call. And here at meta position chlorine will be there. So what it will do, this MCPB, it is a good oxidizing agent. It will give oxygen, right? So but we have studied, I don't know whether you know or not. So if we have anything like cis alkene, if I add this MCPBA, I'll get this epoxide, right? Like this epoxide I will get, right? Epoxide I will get, right? Similarly, there is one more reaction, like see, here I have methyl, let us assume, and here I have hydrogen, or I can take any ethyl, right? To this I add same MCPBA. Here also I have added MCPBA. Here also I have added MCPBA. Here it is ketone. Ketone will be converted to esters. But thing is, see, here methyl is there, here ethyl is there. Methyl and ethyl. Whether oxygen comes here or here, right? That is important. And there is a migratory aptitude. When we discuss, this is nothing but Bayer's vinegar oxidation reaction we call, right? So there the migratory aptitude will be hydride, next comes phenyl, tertiary, secondary, primary. So since this methyl is primary and this ethyl is secondary, so migratory aptitude of ethyl is more. So oxygen, if you see, it will add here only. Here methyl will be there as it is, here oxygen comes, and this ethyl. This oxygen will be given by this MCPBA. Here also epoxide alkene is there. We get this epoxide oxygen that will be given by this MCPBA. Same thing, right? So when ketone is there, we get epoxide. When we have, alkene is there, we get epoxide. When we have ketone, we will get esters here. Right? So these reactions, I hope I have done videos. I think those are available in my YouTube channel. Just check it, right? So, but here to this MCPBA we are adding which to this compound. So here we have alkene also, we have ketone also. Whether we will get epoxide or we will get ester, this thing you should remember. See, here we will get only ester. See, this carbon if you see, this is tertiary, and this carbon if you see, this is secondary. So whenever we add this MCPBA, oxygen will add here only, right? Because it is tertiary, because migratory aptitude is tertiary, secondary and primary, right? So tertiary we will get epoxide, not epoxide, esters we will get. So here oxygen I will write, and here we have ketone same as it is, and other things I will keep as it is only, CH2OMe, and here pi bond I will keep as it is. This alkene doesn't convert it to this epoxide. You will ask, sir, why only this ketone converted to ester, why not this alkene? That is the common question, right? The reason I will tell. See, whenever we have ketone and alkene, we should give preference to this ketone. Ketone will be oxidized to this ester. That thing you should remember. If instead of only simple alkene, if I have this kind of alkene, see here, substituted alkene, here also methyl, here also methyl, then there is possibility we will get epoxide. This ketone will remain as it is only, right? Other things we keep as it is. This ketone will remain as it is, but here what we will get? We will get epoxide. Like this epoxide we will get, and below methyl will be there. These two methyls. Epoxide ketone will remain as it is. So what you should understand, if alkene is there, that too electron rich like methyl are there, substitution, right? When electron rich alkene is there, then only epoxidation happens in presence of ketone. Otherwise, if the simple alkene is there, right, simple alkene only hydrogens, then ketones will be oxidized to esters, not the alkene. So this is the chemoselectivity you should know. We call it as chemoselectivity. So what we understood? So from here we got this one, right? Let me rub all those things which is not necessary, right? I hope you understood. So this is the structure of MCPBA. I hope you noted it. So this reaction along with me you write it, right? So MCPBA, what I got, let me write it here. So the alkene remained as it is, COMe, and here I got oxygen here, and here I got ketone. So it is ester, cyclic. You see this, you know, this is ester, right? Ester we call. If I have ester in cyclic form, cyclic ester we call lactone, right? So since this is cyclic ester, it is nothing but lactone, right? Yeah, I hope you are getting it, right? Once we know about lactone, once we form lactone, then what we will do, to this they will add NaOH in presence of water. So see, esters reaction, you know, this carbon is electrophilic. Electrophilic means electron deficient. So this NaOH means OH minus will be there, right? So that will attack to this carbon. So this pi bond will be broken and comes to oxygen negative charge. Again this negative charge comes here, and this carbon oxygen bond will be weaker. So it will break. So what we will get? So simply see here. So here CO, again oxygen gets double bond O, but here OH attacked here, right? And water will be there, so OH acid will get. And here what happens? Here oxygen O minus, it will get from water, H2O is there, right? So this proton it will get, so it becomes OH, right? Other things will be as it is, CH2OMe, right? And here pi bond will be as it is, right? So this is the reaction what we will get, right? I hope I have done it rightly. Yes, yeah, it's clear, right? So this is 5-membered ring. Can I write it like this? The same structure I will write it like this. See here, whether I have written it rightly or not, you just see. So this is 5-membered ring, 1 2 3 4 5 5-membered ring. Here this pi bond I am going to show here. So pi bond, right? So this pi bond I am going to show, and here I have OH, single bond OH, single bond and OH here. It is below the plane, it comes below the plane, OH, right? And next to that, see here, this OH, next there is carbon, to that CH2OM is there. So this is the next carbon, to that I have to show CH2, see this is above, right? CH2OMe, CH2OMe, right? And next to that carbon, nothing is there. And next to that carbon, nothing is there, right? From here I have below the plane, this is also below the plane, COOH. You can write COOH also, but here in presence of base, this is acid group means it will give H plus. So CO minus Na plus you can show, because acid base reaction, this OH minus, that H plus will form water, Na plus will remain as Na plus, and O minus will remain as it is, and it will be stabilized by this resonance. That thing you know, I should not tell it, right? The same structure I wrote like this. So 5-membered ring, COMe, and everything with stereochemistry I have written. To this, if I add Ki3, right? So here alkene is there, iodine will add. So how it will add? Just it will add like this. See, though this is 5-membered ring, and here above the plane OMe we have, below the plane CO, O minus is there, and iodine will add above this iodine. So I can iodonium ion, you have studied I think. Addition, alkene, when they give addition reaction with electrophile like I plus Br minus Br plus, they will form this iodonium ion, and here OH, everything is there, right? So this O minus is there, so it can do, since it is very near, it can open this iodonium ring, this 3-membered ring, right? Iodine carbon, this is we called it as iodonium, right? Iodonium ring, and this iodine we call it as iodonium ion, because it is having positive charge, right? So ion it is, right? So here ring opening happens because this electron density O negative is there, it will attack to this carbon, the ring opening happens. Here 1, 2, 3, 4-membered ring it will form, right? 1, 2, 3, 4, yes. Sorry, I have missed one thing I think. Yes. Here I should tell, see, this CH2 COH is there. Directly I have written COH. Here CH2, one more CH2 group is there. This is the problem. See, this CH2 group I was missing. So here CH2 group I should show, because it will form 5-membered ring. 1, 2, CH2 group 3 and 4, and this is 5. I was writing 4-membered ring, so I got confusion. How it 4-membered ring? Because ring formation, whenever it is there, it will form only 5-membered ring. It is thermodynamically more feasible. So here CH2 group is there, and above I have CO O minus. Now this O minus will attack to this carbon. Now see, 1, 2, 3, 4, 5. 5-membered ring formation is thermodynamically more stable, right? So I'll rub all the above things, right? So that will be clear to you. So nicely I made you understand. I hope you are getting it. Just let me rub all the things, right? So till this everything is clear, right? Yeah. So now let us see. So from here what I will get? It is 5-membered ring. Here I have OH. Here above the plane I have CH2OMe, and here I have below the plane CH2CO. Since it is below the plane, it attacks below the plane only. This iodine is above, it will come above only iodine, and it becomes neutral. As it got this electron density, iodine plus was there, it became neutral, and I got this compound, right? For this, then what I will add? I will add this, to remove this iodine, what I will do, I will add this Bu3 SNH. So this SN, tin is there, right? Tin iodine bond is very strong. So it will take this iodine and it will give this hydrogen. So it will form radical mechanism. Through radical mechanism, they will form like homogeneous breaking will happen. Here radical will get, H radical will attack here, and I will get H bond here. So here H comes. That iodine will be bonded with this. So like this the reaction happens. Right, other things remains as it is only. OH, OMe, right? So nothing much difference. But here what they did, along with this Bu3SNH, they added this acetic acid Ac2O in presence of pyridine. So that this OH is there, right? This pyridine take this H plus, O minus will attack to this acetyl. Like that they protected this alcohol OH as they protected like this OAC, right? So the simple reaction they did, right? So once they did, then what they did, they added this one. What the structure it is? BBr3 in presence of CH2Cl2, dichloromethane, DCM we call, dichloromethane, that is a solvent during at 0 degree Celsius, right? So first step, what it will do, see the reaction I will tell, all this I will write it as R till the CH2 and OH is there, CH2OMe, let me write like this, OMe, this all is R, CH2 CH2OMe, right? To that, if I add this BBr3, see, B boron is there and bromine. So all these are electronegative, will show minus I effect, because of which it will be having empty p orbital. So it will be electron deficient. So this lone pairs are there, right? They will attack here. It lone pair will be given to this boron. Boron gets negative charge and this oxygen gets positive charge. So R CH2O Me, and here oxygen gets positive charge, boron gets negative, and here Br and Br, right? So Br, these are halogens. Bromine is a good living group. It leaves the system with electron density, so it will leaves as Br minus. So it became neutral now, right? Because negative charge it took along with that Br minus. Then what it will do? This Br minus will attack this methyl, and this electron density will be taken by oxygen. Initially it was positive charge, now it becomes neutral. So what we will get? I will get R CH2O Br like this, plus methyl attacked to with this CH3. Methyl means CH3, right? Br, CH3 Br. So these are the product I will get, right? Alright, so this is the product I will get. To this, with this reaction, right? Further, if I add water, right? So after all this reaction, they end up with this, right? To this, they will add water, protonated water. So what happens? This bond will be broken. H comes here. OH will attack to this BBr2. So it will form alcohol RCH2OH. Plus, along with that, it will form boric acid OH, OH, and OH. Boric acid we call, right? S3BO3. Boric acid, like that. So what we will get? We will get RCH2OH. This bond will be broken. So this reaction, I hope you got it, right? Since we got this reaction, I am going to write directly the product here. So from this, what I will get? This OMe is there, right? Instead of OMe, I will rub it here only. I will get alcohol OH, right? That methyl is removed. I have some more minutes. Let me explain it. Few more points, right? So once we got that, then what we will do? We will add some oxidizing agent. Mild oxidizing agent. Mild oxidizing agent. Why only we use mild? Because I will convert this ketone, this alcohol CH2OH to aldehyde. If I use any strong oxidizing agent, that won't give me this aldehyde. It will directly give me acid. Acid means COOH. But I want this aldehyde, so I will use mild oxidizing agent. Which one I will use? Let me give you the name. So I will use a mild oxidizing agent, and that is CrO3 in presence of 2 molecules of pyridine and solvent CH2Cl2, and the reaction at 0 degrees Celsius. Because of this compound, it is a mild oxidizing agent, and I will get oxidized product, that is aldehyde. I will write it like this simply. See how nicely I got this product, CH2, right? And here hydrogen is there. Let me not show that. Now it is OAC, and here CH2 aldehyde I will get COH. CH2, this is CH2, OH is there. Here double bond I will get COH. So you know, right? Primary alcohol will be converted to aldehyde in presence of mild oxidizing agent. Secondary alcohol, if I have, it will be converted to ketone. So this is primary, right? OH attached to only one carbon, so it is primary carbon, and this alcohol we call it as primary alcohol. So it is converted to aldehyde, right? So for this class, let we stop here only. In next class, let me continue with that the aldehyde, right? So till then, take care and have a great day.